So in today's video, we're going to go ahead and delve into u-substitution. So now that we've kind of covered all of these different basic functions and their integrals, now we're going to actually start looking into more methods of integration. And u-substitution is a very crucial method that we're it's one of the more basic methods, but it's one that is applicable to really all fields of calculus. And it's something that students oftentimes struggle with. So we're going to stick to substitution for, 4 or 5 videos to really get comfortable with it before we delve into more techniques of integration. And so suppose we wanted to evaluate this integral right over here. And really the best way to introduce u-substitution is to kind of look at a more concrete example. So suppose we wanted to integrate, we wanted to take the indefinite integral of 2x over x squared plus 1 dx, right? So this is a rational function. We have a 2x in the numerator and x squared plus 1 in the denominator. And so essentially we don't really know any kind of way to immediately integrate this. We kind of have to think a little bit. And so u-substitution essentially allows us to replace x with a different variable, u, and u is kind of just any dummy variable. And essentially, sometimes when we rewrite this integral in terms of another variable, then it becomes a little bit more, or a little bit easier to integrate. And so let's actually go ahead and do that. So let's define this variable u. So let u, and really we should call it u of x, right? But we're just going to omit that x, because this is going to be written in terms of x. It's going to be written as a function of x. So let u equal to what? What do we want u to be equal to? Well, I mean, we have this 2x in the numerator. We have this x squared plus 1 in the denominator. It might be helpful to set u to be equal to x squared plus 1, and we will see why in a moment. So let's have u be equal to x squared plus 1, right? And then what happens if we want to take the derivative of u? Let's go ahead and differentiate u. So if u is equal to x squared plus 1, then du by dx, right, the derivative of u with respect to x, is simply 2x. And so we have u over here, x squared plus 1. We have the derivative of u with respect to x, which is equal to 2x. Now, what can we also do? We can also multiply both sides of this by dx, right? I mean, it's a little bit kind of, it's not very formal, but it's a good intuition. We can think of kind of multiplying both sides by dx, by this differential, and then the dx's will cancel out, and then we ultimately will end up with du is equal to 2x dx. And so now we have these different relations. We have u is equal to x squared plus 1, du is equal to 2x dx. And so now let's look at our original integral. Essentially in our original integral, let me rewrite this down over here. So we had the integral of 2x over x squared plus 1 dx. Well, you might notice something. What is x squared plus 1? Actually, I'm going to go ahead and change colors just for, just to brighten up this page a little bit. Let's take this blue maybe. Yeah, I think that's a nice color. So over here we have an x squared plus 1 in the denominator. But what is x squared plus 1? X squared plus 1 is just u, right? U is just x squared plus 1. So we can rewrite this as the integral of 2x over, in the denominator we used to have an x squared plus 1, but now we just have a u, right? Because u is equal to x squared plus 1, and then we can't forget the dx over there. But now we have two different variables. This is a little bit more complicated. So what can we do to kind of further simplify this? Well, we have a 2x over here, and we also have a dx. So what can we do? We can kind of take this dx and put it next to the 2x over here, right? Because they're both in the numerator, so we'll end up with 2x dx in the numerator, and we have a u in the denominator. I don't know why that line is coming out kind of tilted at an angle. Okay. So we have 2x dx in the numerator, and we have a u in the denominator. But what is 2x dx? How do we describe that in terms of u, or in terms of like the differential of u, du? Well, we know over here from this relation that we derived that du is equal to 2x dx. So we can kind of just take this 2x dx and substitute it with du, right? So this ultimately becomes the integral of du over u. So we didn't really change the integral, we kind of just simplified it and described it in terms of another variable. We didn't change what the actual integral is, but we just described it in terms of another dummy variable u. And you can use any variable you would like, but u is kind of the generally selected variable. And so this is what u-substitution is. We kind of replace x with another variable u that kind of simplifies the integration process. We substitute x, or we describe the integral in terms of u, right? We change the variable from x to u, and then we kind of simplify. That just simplifies the integration process. And so now we know what this integral is, right? It's just the integral of 1 over u times du, which is just the natural log of u plus c, or we could say the absolute value of u if you would like. Let's actually do that. So the absolute value So the natural log of the absolute value of u plus c. But we started off with our integral in terms of x, and now we have the final answer, the antiderivative in terms of u. So if we want to kind of go backwards, we just have to resubstitute. We know that u is equal to x squared plus 1, and so if we want to substitute that back in, then the natural log of the absolute value of u plus c, what's that going to be equal to? That's the natural log of the absolute value of x squared plus 1, and then that plus c kind of stays the same, right? We just substituted. U is equal to x squared plus 1, so when we want to kind of unsubstitute, we take the u out, and now we describe u in terms of x to have our final answer, our antiderivative, as a function of x. And since it's an absolute value, we don't really, or since it's x squared plus 1, which is always positive, we don't really need the absolute value. So our final answer over here is the natural log of x squared plus 1 plus c. And you can verify that. You can take the derivative and you'll end up with 2x over x squared plus 1. And essentially, this is really what u-substitution is all about. There's going to be much more complicated examples in the future, but for now, all you need to think about when it comes to u-substitution is kind of just taking the integral and describing it in terms of another variable, which helps simplify the integration process. And we're going to look at plenty of examples in the next video to get much more comfortable with this notion because it is extremely important. It's, like I said, one of the more basic integration methods, but it is one that we'll be using throughout this entire integral calculus course.